All right, these notes here are on competition. Competition has a lot to do with density. And so, when we talk about density, we are talking about how many organisms there are per unit area. So, the more organisms that you have per unit area, the more stuff you need to keep them alive. And so, more dense populations have more organisms. So density is just like how many, like in this box, how many dots are there? If these represent organisms, are there more dots here or here, or they can be, dispersed differently. But this is population density. So how many organisms live in an area? And when we look at the United States here, population density can refer to people. You're an organism too. So you can see that over here on the West Coast, California has the larger population density. So there are more people per square mile in California than there are in Oregon or Nevada or Arizona. And you can see the most population density over here, like in New Jersey or Rhode Island, has high population density. Um, Individual cities have different population densities. So, like LA is a significantly more population dense city. People live pretty close together, but New York is way more dense because people tend to live in high-rise buildings. And there just tends to be a lot of people in an area. So New York City is the most population dense city. So density just means how many people are there in a unit area. So, what affects population density? Why would there be more people in one area and not in another? So, it could be climate. That's a large part of what it is for people. So, people like it when it's not too hot and it's not too cold. So, areas of the United States where it is not too hot and not too cold, they tend to be pretty population dense. An example of that would be like coastal California. If you live in San Diego, it's not too hot and it's not too cold most of the time. So, it's a nice place to live. And so, a lot of people congregate there. Are there enough resources? So, is there food? Is there water? Is there shelter? And this is not just people, this is animals as well. So, a desert is going to have a low population density because there's low water and low shelter and low food. It doesn't have a lot of resources. Same thing with like the Arctic tundra that's all frozen over in the winter. Low food, low water, low shelter, so you're not going to find a whole lot of organisms living there. Number of predators can influence an ecosystem as well, even if this ecosystem is like, oh, this is amazing. If it's full of predators, you're not going to stick around. You're going to find somewhere else to live. So number of predators influences population density as well. And if organisms do not have the right resources or climate, usually what they do is they die or they migrate to a different area where they can find better access to better climate or better resources or fewer predators. So some factors are density dependent. What this means is this is a limiting factor. We've talked about limiting factors before, and a limiting factor is anything that like reduces your ability to survive. So if it's a density dependent limiting factor, it's one that gets worse when there's more of you and gets better when there's fewer of you for the most part. So if the population is large, whatever this factor is, it's worse. And if the population is small, then this factor isn't as bad. And so density dependent factors don't tend to affect small scattered populations as greatly as they do large concentrated populations. Some examples of that are competition. So if it's crowded in the area where you live, you are more likely to have to compete for food and water and space. If it's just you and a couple other zebra, no big deal. You don't have to compete with each other because there's plenty of resources and there's not very many of you. But when it gets crowded, there's more competition. So the resources start to get limited and you start to fight more over them. There can be intra-specific competition. This is where you're competing with members of the same species. So you are competing with your exact same species for the exact same resource. So intra-specific is same species.
Gray kangaroo marsupials live out on the relatively well-watered grassy plains. They are among the most sociable of all Australian marsupials. But living in groups can lead to problems in getting on together. Last season's joeys are fast approaching independence, which means that their mothers will soon be ready to mate again. Males use their sense of smell to find out if a female is sexually available, and will court her for several days. Having found one who seems to be promising, a male stays close to her side to try and ensure that he and no other male mates with her. The most dominant male is likely to be the one to father most of the next generation, and that is something worth fighting for. Joeys also fight, but it's just play boxing, a way of learning skills that will be important in later life. But it's not always a fair fight. Fortunately, this little one still has mother to see off the neighbourhood bully.
Right, and then there's inter-specific. So the other one was intra, this one's inter. And this is where you compete with different species, usually because you guys use the same kinds of resources. So this chipmunk here is trying to enjoy this, looks like some sort of seed or nut, and these birds also want the seed or nut. And so you have to compete because you eat the same food and live in the same area.
Mantids will eat anything that moves, including other mantids. Time to leave. This tiny insect is now open to attack from predators lurking in the undergrowth. Whether an individual mantis survives or not is partly a matter of chance. Whether it's spotted by a predator, whether it turns right or left. So far, its luck has held. But this hungry jumping spider is still in pursuit. A mantis is born with exceptional eyesight, but the spider's is even better. Although this young mantis can't yet fly, its long forelegs, evolved to catch prey, give it reach. There seems to be no escape. But this mantis has a surprising line in self-defense. Kung Fu, praying mantis style. Of course, it's all bluff, trying to look bigger and confuse its enemy. But it's got away with it. Just staying alive for its first few hours is a significant accomplishment for a newly hatched insect. But there's still a long way to go. With a bit of luck, in 2 months' time, it will be as big and beautiful as this orchid mantid. Or maybe not. After all, mantids are cannibals.
Alright, so the competition there in that mantid video was between the jumping spider and the bigger orchid mantis, who are both trying to eat the same little mantid. So something else you will learn about this week is something called competitive exclusion. So like we've said before, the niche is like your job in the ecosystem, and no two organisms can have the same niche. If you do, you'll compete with each other until one of you is removed. This is called competitive exclusion. So when there is interspecific competition, this is two different species, and the two organisms share the same niche, one will be eliminated from the habitat. Usually the one that has a slight advantage, maybe it eats faster or it needs less energy, that will be the one that is successful. And the example here is always between these two, and you have a lab on this this week, these two paramecium, which are single-celled organisms. Do I have a picture of them? No, I don't. So you have one of them, so right here they're both introduced into the same ecosystem. So you can see their lines are the same, you put the same numbers in. And then they kind of grow together, but then they start to compete with each other, and you'll see that one of them survives and goes up, and the other one dies and goes down. And so this is competitive exclusion. This is what that graph is going to look like when you do this lab later this week. So somebody does well, somebody dies. This is when organisms use the exact same food in the exact same environment. And then there are density-dependent factors. So these are factors, or we're already talking about density-dependent factors, but another one is predation. So when a population gets big, you're more likely to get predators. So the more crowded your population, the more likely you are to attract a predator, and then it will come in and start eating you. So a shark isn't going to be attracted to a school of like 10 fish. It's going to be attracted to a school of like 100 fish because it makes it more likely it's going to catch some food. So that's why predation is density dependent. You're more likely to get eaten. Well, I mean, overall, your individual risk of getting eaten is actually lower when you're in a group, but you're more likely to attract a predator in the first place. We'll talk about predator-prey graphs this week. So you have an assignment where you're doing a predator-prey graph, and predator-prey always go through these cycles here. Like we call these boom and bust. And when you see your predator-prey activity, you'll see this as well. So the prey goes up, like prey is increasing, increasing, increasing. You attract a predator. The predator is living the good life because he's eating the prey, so he's also increasing. And at some point in time, the predator gets large enough that it starts to decrease the prey population. So the predator going up decreases the prey. And then the prey goes down, and the predator in response goes down as well. And then once the predators are almost gone, then the prey can go back up again because the predators are gone. And then the predator will go back up because the prey went back up, and so on and so forth. And so you can see they go up and down and up and down, and they increase and decrease alternatively. Another density dependent factor is parasites or disease. If you live in a larger group, you are more likely to get sick. If it's a small group, there's fewer of you, you're less likely to get sick and less likely to spread that disease to other organisms in your group because you live farther apart from each other. But if you live in a large, crowded group, you're more likely to spread disease. Or it could be parasites like ticks. Ticks can jump from dog to dog to dog if dogs live close together. And then density independent factors. These are things that don't really change based on your size, but they do limit your ability to survive. So it could be weird weather, like you get in a really cold winter or a snowstorm or a heat wave. That's not going to matter based on how big your population is. The weather doesn't care, but it will influence your ability to survive, just it won't change based on the size of your population. Any natural disaster, like a hurricane or a volcano eruption, it's density independent. It's not really going to affect the eruption itself. The volcano eruption itself is not going to change based on there's a large population living on the volcano or a small population. And then there's seasonal cycles, like it's cold in the winter, it's, more water in the spring, those sort of things. Mostly these are weather related, things that are nature related, and weather, they don't tend to influence or don't tend to be influenced by the number of organisms in a population. So they are density independent. All right, so here's an example for tadpoles. So let me kind of explain what we're looking at here. So this is the body mass of tadpoles, so like how big they are, and then the time in weeks. And so what you're seeing here is this darker line is more tadpoles. There's 160 tadpoles in this pond. And so you can see that these tadpoles, they are smaller. And then as we reduce the number of tadpoles, so here there's only 60 tadpoles in the pond. Here there's only 40 tadpoles in the pond. And here there's only 5. So the 5, you can see that that one gets bigger than the others. And so what this is showing you is more competition. So this one is more competition because there's more of them. This leads to smaller tadpoles overall. So the more an organism has to compete, the fewer resources it ends up getting because competition costs energy. It costs resources to have to fight with other organisms. Whereas if there's very few of you or resources are abundant, then you tend to get more of them and you grow larger. Here is an example with corn. So this is the yield that you get per plant. So this would be a higher yield up here, and this would be a lower yield down here. And down here it says population density. So this is fewer plants over here on the left, and this is more plants over here on the right. And you can see there's a pretty direct correlation there. So the more plants you plant over here at 100, the fewer the less corn you get out of that. So more plants gives you less corn. And then if you plant fewer plants per acre, then you get more corn. So again, this is due to competition. As organisms have to compete for resources, everybody ends up just getting a little bit less. And with plants, those resources are not fighting with each other, but they are instead access to water, access to minerals in the soil, and then access to sunlight. But as they have to compete for those resources, you can see you get less stuff. So competition affects plants too. The more corn plants around, the smaller the corn grows because of competition for resources.